Yes, the next topic is linear combinations. Yeah, this is just another thing that we can do. Now we have these two operations we can do. We can do addition of vectors and we can do scalar multiplications. And using those two we can do something called a linear combination. Multiplication. Oops. No. So we say we have a set of vectors. We have a bunch of vectors. We call that S. And just to call those, like we call them V0, V1, V2, etc., 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 Vn, like this, a little bit bigger. Based on those and a bunch of numbers, we can then make a linear combination. And all of this, the result of this whole thing is a vector. It's a single vector. So we just multiply each number by each vector, basically. Like this. Like that. The point of this whole exercise is that we can choose these numbers sort of arbitrarily, and then we actually get a kind of space from this. So imagine that we vary all these numbers. We keep the vectors the same, but we vary all the numbers like they can be varied at all. And what that gives us is it spans a space. So the vectors actually span a space in this way. Linear combination. And just to get the terminology completely correct, this is called a linear combination of the vectors in S. So let me just put this S just to be clear about that as well. Something like this. Suppose oops, we have a set of vectors S. This. Maybe a little colon to make that clear as well. And another red line. Pretty simple. There's nodding. That's good. Based on this topic, we can talk about something called linear dependence. And this is sort of an important property of these spaces that are spanned by a linear combination. This. Yeah, I'm just going to put something that looks like a definition here. suppose we can express one of the vectors, any of the vectors in this S, this set of vectors that we have. So we could maybe have one of those, and it could actually be expressed by making a linear combination of all the other vectors, but not this one. So if we get to the same point by doing that, by using all the other vectors, then we say that this set of vectors is linearly dependent. So it has linear dependence. It's kind of like it's redundant in a way that we didn't really need that vector. We could actually do without it to span the same space. That's what it means. I'm just going to try to write the notation for that. So we have, maybe we say it's vector 1 in this set, and it could actually be of course it might be a big set, so I use this n notation again. The point is that if it's possible to do this with any, we could choose some scalar values for these a's so that this would be true. Then if that was at all possible for any set of values for these, then we say that this set of S is linearly dependent. Linearly dependent. That's what it means. There. I'm just going to try to illustrate with these drawings what I just said. So for instance, if we have a very small set here of two vectors, if we do a linear combination of those, we will span the entire plane. So we could find any point in the entire plane by choosing the appropriate linear combination of those. These are not linearly dependent. Oops. Because you cannot take one out and then use the other one. There's two, right? So you cannot, if we want to get to this point, we cannot do that using this by multiplying it by any number. That's impossible. So therefore, this is not a linearly dependent set. This is linearly independent. But if we draw another example, which is linearly dependent. So if we have two vectors that have sort of the same direction, for instance, to make sure that they actually have the same direction, like this, and then another one like this. Just remember to write what I say. Yeah, this set is linearly dependent because it's possible to take one vector out and use the other one's linear combination to get the same vector. And again, you must remember that it's not about positions in space; it's a displacement that has to be the same. So even though these are drawn in separate places, they can be drawn on top of each other or somewhere else. It doesn't matter. Yep. And now we get to this, the representation of vectors, which you may be more used to using a set of coordinates. What does this? That. Yeah, we define something called a basis, and we use a set of linearly independent vectors. Important word here is, of course, basis. There. So I'm gonna draw this, an example of this. This would probably look familiar. Like, I just draw 3 vectors. And they are, you should imagine this is 3D. It's like a coordinate system in 3D, so the final arrow is actually pointing out from the screen. And of course we use the normal denotations for these so we can recognize it. X, Y, Z. But in this case you think of these as 3 vectors. We call this a basis. And they span a space, a 3-dimensional space, so you can do a linear combination of them and choose some numbers, and then you can get to anywhere in a 3D space. So in this anywhere we call this V, this anywhere we want to go. Oh, I made a mistake. It's a more mathematical way of doing it, is distinguishing between the, sorry, we'll call this ijk instead. Like this. X, Y, Z is used for the scalar values. So once again, okay. So we use some scalar value x times I, the vector I, some scalar value y times j, and some scalar value z times k. And let me just put denotations on it. Just to see what is vectors and what is scalar values. ijk are vectors, x, y, z are scalar values. There are a few more assumptions that need to be met for this to work, and that is that the ijk are of unit length 1, and also that they are perpendicular. This perpendicular is not going to go into the definition of that. It's a mathematical term, but you all probably know what it means. It's just, it has an easy intuitive understanding of it. But that's another, just to be clear that for this to be correct. And all this leads up to is simply that we can define what the coordinate representation of vectors is. X, Y, Z. I'm going to write them in this way, horizontally. It's easier to write, and with parentheses around going forward. Yep.